Welcome students to the paper of numerical methods in the subject of information technology under EPG Pathshala. Today we are going to focus on the topic of finding roots of polynomial. You will wonder, why do we need to find especially roots of a polynomial? Aren't roots special function of aren't polynomial special case of function? And so, the methods for obtaining roots of f x equal to 0 can be applied to finding roots of a polynomial also. Why should we need separately, specially the methods for finding roots of a polynomial? So, the answer which automatically comes to one's mind are many. See, the first thing is that in case of general f x equal to 0, not much is known about the location of the roots, and moreover, see those equations which one comes across in the scientific and physical applications, usually one is interested in finding some constant which may be of the order of 10 raised to minus 12 or very high. So, the range, the domain, the range of the constants are quite known. In case of polynomials, when one encounters, then many times one is interested in knowing all the roots of the polynomial, like eigenvalue problem, or in the case of Gauss quadrature and even in numerical other integration and differentiation formulas, one comes across a polynomial whose roots are going to be used in the formulas, and therefore, one is interested in knowing all the roots of a polynomial. And luckily, there is a fundamental theorem of algebra which tells that if we have a polynomial with real coefficients of degree n, we are only going to consider polynomials with real coefficients, then it has exactly n roots. These n roots may be real or complex, and a root of multiplicity m is counted m times. Like for example, if I have a polynomial x minus 1 square equal to 0, namely x square minus 2 x plus 1 equal to 0. So, it has root 1, but this root 1 is counted 2 times, because x minus 1 into x minus 1 equal to 0. So, this root 1 is of multiplicity 2. So, the fundamental theorem of algebra tells us that a polynomial of degree n has exactly n roots if the root, considering the root of multiplicity m should be counted m times. So, this is one great advantage. Moreover, see in case of polynomials, there is one more point, that if x 0 is the root of polynomial p x, then x minus x 0 is a factor of p x, and if x minus x 0 is a factor of p x, then in that case we can write p x as x minus x 0 into q x, and this degree of q x is going to be n minus 1 if degree of p x is n. This q x is called deflated polynomial, and roots of x 0 is one of the root, and all remaining roots of p x are going to be the roots of q x. So, here if you have obtained one root of p x, then we can obtain deflating polynomial just dividing p x by x minus x 0. That can be done very easily iteratively. We will see in the next module how to do it, and then just the problem reduces to finding roots of q x, which is called deflated polynomial, which is of degree n minus 1, and that is how one step by step the degree of polynomial goes on reducing, the problem goes on becoming easier and easier, and that is how all the roots of a polynomial can be found very easily. And second aspect is, in case of polynomial with real coefficients, if the roots are real, fine, and the roots are complex, then these complex roots occur in pairs. So, if a plus I b is a root, a minus I b is also a root, where a and b are real numbers. And therefore, see in the case of polynomials, there is one more thing, that there are special methods available for isolating the real roots of a polynomial. The advantage of this is that we can know very well that where the roots are located, and so we can know the intervals under which the root lies, and then end point of those interval or the middle of the point of that interval can be taken as an initial guess for finding the roots by using the iterative methods which we have already studied, namely bisection, false position, Newton-Raphson, secant, successive, and many other methods. Any of them can be used to find the root correct to desired accuracy. See, such type of results are not available in general to general function f x equal to 0, but for polynomials there are many results which are available, and we will take them one by one. The first one which we would like to take is known as Descartes' rule of sign. It was given by Descartes in 16th century. So, let us take a polynomial p x of degree n given by a0 plus a1 x plus a2 x squared so on, plus a n minus 1 x raised to n minus 1 plus a n x raised to n. A n must be different from 0 because it is a polynomial of degree n. Now, this Descartes' rule of sign tells us that the number of positive roots of p x is either equal to the number of changes in the sign of the coefficients a0, a1, a2 taken in that order, or less than that by multiple of 2. See, this Descartes' rule of sign tells us about the how many possible positive roots are there, and that is, first thing is you have to write the polynomial in a particular increasing order of the power of x, or other way also we can write in the decreasing power of x, and then we observe the change in sign of the coefficients a0, a1, a2, an. If this number, whatever we number get, the number of positive zeros is equal to either that number or less than that by multiple of 2. Let us understand by an example. Let us take the polynomial p x as given by minus 6 plus 10 x minus 6 x square plus 4 x raised to 4. Coefficient of x cube is 0. So, here a0 is minus 6, a1 is 10, a2 is minus 6, a3 is 0 and a4 is 4. Let us look at the change in sign. See, a0 to a1, there is a movement from minus 6 to 10. So, sign has changed once. Again a1 to a2, the movement is 10 to minus 6, one more change in sign has occurred. From a2 to a3, there is no change in sign because 0 is there, we do not count it as a change in sign, and from a3 to a4, that is minus to 4 or 0 to plus, it has moved. So, there is one more change in sign. So, in all, if we observe from a0, a1, a2 to a3, a4, there have been 3 changes in sign. And so, by Descartes' rule, the number of positive roots of the polynomial would be either 3 or 3 minus 2, because see the complex roots occur in pair. So, either 3 positive roots or 3 minus 2, that is equal to 1 positive root. So, there is at least one positive root, but we do not know whether 1 or 3. Now, see, as far as the Descartes theorem is there, Descartes rule is concerned, it only gives us the number of positive roots, but then we can use it to even apply to determine the number of negative roots as well. Let us see how we can do it, and for that it is very simple. We know that the positive roots of p of minus x will be the negative roots of p x, and therefore, if in the expression of p x we replace x by minus x, obtain the polynomial p of minus x and apply Descartes rule to p of minus x, then the number of positive roots of p of minus x, whatever inference we draw, is nothing but the estimate for the number of negative roots of the polynomial p x. So, let us take the same example and apply our method to determine the negative roots of p x. So, our p x was minus 6 plus 10 x minus 6 x square plus 4 x raised to 4, replace x by minus x. So, p of minus x becomes minus 6, x becomes minus x, so minus 10 x minus x square or minus x square is same x square. So, minus 6 x square plus x raised to 4 or minus x raised to 4 is also x raised to 4. So, plus 4 x raised to 4. giving us p of minus x is minus 6 minus 10x minus 6x square plus 4x raised to 4. And now, if we look at the change in sign, a0 is negative, a1 is negative, a2 is negative, a3 is 0. So, there is only one change in sign when we move from a3 to a4, and so there is only one change in sign, giving us that p of minus x has exactly one positive root, giving that our polynomial px under question has one negative root. So, about negative root, the number is fixed, it has one negative root, and about positive roots, what we have obtained is either 3 positive root or 1 positive root. So, scenario is 1 positive root, 1 negative root and 2 complex roots, or 3 positive roots and 1 negative root. So, this is the inference we have been able to draw from the previous example applying Descartes' rule. See, many times the Descartes' rule can be more conclusive, depends upon the example, depends upon the polynomial under question. Let us take second example, second illustration, where px is given by x raised to 4 plus 2x square minus x minus 1. See, in this case, see, as I said, we can move from higher degree terms to the lower degree or the lower degree terms to higher degree. The only thing we have to keep in mind is that we have to keep them in the order. So, here see, a0 is minus 1, a1 is minus 1, a2 is 2, a3 is 0 and a4 is 1. And so, see, from negative to 1 there has been only one movement, there is only one change in sign. So, we can say that this px has exactly one positive root. Now, let us determine number of negative roots also. So, change x to minus x in the expression of px. So, p of minus x becomes x raised to 4 plus 2 raised to x square, because even powers they give the same values, and minus x becomes plus x minus 1. And here again a0 is minus 1 and all other terms are positive. So, there is only one change in sign, and therefore, p of minus x has one positive root, and so our polynomial under question px has one negative root. So, we have obtained px has one positive root, one negative root, and by fundamental theorem of algebra px has 4 roots because it is polynomial of degree 4. So, other 2 roots have to be complex conjugate pairs. So, the Descartes' rule is very easy to apply, but since it is easy, it only gives us information about positive roots and negative roots. It does not isolate the roots, it does not give us idea about how many roots lie within any particular interval a b. There are more stronger results, but the only thing is there is no gain without any pain. They are little more laborious, we have to work little harder in order to apply them, and they give us more information, more clues about the roots of a polynomial in a given interval. So, let us take them one by one. Let us understand the next result, which is known as Budan's theorem. See, Budan's theorem statement is, let us say we are interested in knowing the root in the interval a b. We need to determine all the derivatives of px. Polynomial of degree n, determining derivatives are very easy. It is very easy to differentiate polynomial and get the expression of the derivatives. So, let pk denote the kth derivative of px, and pk at the point a be the value of the kth derivative of the point derivative of px at x equal to a. Now, let v suffix a be the number of changes in the sequence of the numbers p a, first derivative of p, second derivative of p, so on up to n derivative of a. Then the theorem says number of roots of px in the open interval a b is either equal to the absolute value of the difference v a minus v b or less than that by multiple of 2. What is v a? v a is the number of changes in the sign of the value of p a first derivative, second derivative, third derivative up to p n derivative at the point a, and v b is similarly the number of changes in the sign we have observed from the value of p at b, first derivative at b, second derivative at b up to n derivative at b. So, once we obtain v a and VB, take the difference and the absolute value. So, this gives us the upper bound on the number of roots which lie in the interval AB, and not only that, it also tells us either the number of roots are given by that figure or less than that by multiple of 2. Let us take the same example which we have considered just now in the case of Descartes' rule of sign, namely p x given by minus 6 plus 10x minus 6x square plus 4x raised to 4. See, we want to apply Budan's theorem. We need to determine all the derivatives of p x. So, let us do that. P dash x is given by minus 6 is constant, derivative is 0, 10x, derivative of x is 1. So, I get 10 minus x square, derivative is 2x. So, minus 6 into 2x, that is minus 12x, plus derivative of x raised to 4 is 4x cube. So, I get 16x cube. So, first derivative is 10 minus 12x plus 16x cube. Similarly, let us find second order derivative. So, p 2 x is, we differentiate p dash x 1. So, we get the second derivative of p, 10 is constant. So, it becomes easier and easier to get the successive derivatives. So, minus 12 plus derivative of x cube is 3x square. So, 48x square. Differentiate this again. So, p 3 x is given by minus 12 is constant, derivative is 0, 48 into 2, that is 86x, and finally, 4 derivative of p 4 x is 86, and fifth and higher derivatives would be 0. So, with these values of p, now we need to evaluate all these derivatives at the interval at the point a and b within which we want to know the result. Let us try to work on the intervals minus 2 to minus 1, minus 1 to 0, 0 to 1 and 1 to 2 just for illustration. Meaning by we are going to apply the Budan's theorem to know about, to interpret about the number of roots that may lie in the interval minus 2 to minus 1, in the interval minus 1 to 0, in the interval 0 to 1 and the interval 1 to 2. So, we have these derivatives. Now, let us make the table for getting the values of these polynomial and the derivatives. So, let us apply Budan's theorem to the polynomial p x given by minus 6 plus 10x minus 6x square plus 4x raised to 4 to know the number of roots in the interval minus 2 to minus 1, minus 1 to 0, 0 to 1 and 1 to 2. Now, see by our theorem, what does our theorem say? That find the values of p, p dash, second derivative, third and fourth at the point minus 2, at the point minus 1, observe the changes in sign in the sequence, and that is v minus 2 will give you the number of changes in the sign it takes from p minus 2 to derivative at minus 2, second, third and fourth derivative at minus 2. Same way v of minus 1 will give us the changes in sign which occurs from p minus 1, derivative minus 1, second, third, fourth, so on, and the difference, absolute value of the difference v minus 2 minus v minus 1 will give us the number of roots which lie in interval minus 2 to minus 1 and so on. So, that is how let us fill the table and calculate the number of roots which may lie. For filling purpose, the easier would be, rather than fill row wise, column wise filling is more convenient for us. Let us see how. Let us fill the easiest column first, p 4 derivative. And second point is, because we want to know only about the changes in sign, we need not find exactly numbers. All we want is whether the value is positive or 0 or negative. So, let us first do the easiest work, 4 derivative. See, 4 derivative of polynomial is 86, which is always constant positive. So, no matter what the argument is, value is positive, equal to 86. So, here all these become plus, value of 4 derivative at no matter what the argument is positive. Now, then let us fill the third derivative column. p 3 x is given by 86 into x. So, if x is positive, value of p 3 is positive. If x is 0, value of p 3 is 0. If x is negative, value of p 3 is negative. So, here x is minus 2, p 3 will be negative, x is minus 1, p 3 will be negative, at 0 it is 0, I am just, you can take it minus, p 1 it is positive, at 1 p third derivative will be positive, at 2 the third derivative will be positive. Now, come to column for the second derivative. Second derivative is 48 x square minus 12. At 0 it is negative, it is negative minus 12. At 1, 48 minus 12, so it is positive, 48 is higher than 12. So, it is positive, x equal to 2 further higher value, so it is going to be positive. At see, it is the argument x is minus 1, or see, this is a symmetric function because x square is there. So, at minus 1 also same value of the function px to p2 has, at p2 at minus x and p2 at x have the same values. So, again at minus 1 it is going to be positive, at p2 at minus 2 is same as p2 at 2, so it is positive. Come to now first derivative. First derivative at 0, let us first fill easiest case. So, it is 0, 0, 10. So, at 0 first derivative is positive. Now, at x equal to 1, if you look at 16 minus 12 4, 4 plus 10 14. So, this is positive. Further at 2, see 2 cube 8, 8 into 16, and this is only 12 into 2 24, this is also positive. So, derivative at x equal to 2 is going to be positive. This is more higher term, more dominating than compared to other terms. So, this is also going to be positive. Let us take x negative. If x is negative, this is negative, this term will become positive. So, when x is minus 1, it is minus 16 plus 12, x is minus 1, so plus 12 plus 10. So, 22 minus 16, so this will become positive. At minus 2, this is becomes minus 8 x cube. So, minus 8 into 16, 16 into 8 minus 8 into 16, and this is minus 2 into 12, this is plus, but then these two terms are smaller than 16 x cube and this is negative term. So, p dash at x equal to minus 2 is going to be negative. And finally, let us calculate value of p at minus 2 at different points minus 2, minus 1, 0, 1 and 2. Again 0, minus 6, so it is negative. At 1, 10 plus 4, 14, minus 12, so positive. At 2, this is 64, 2 raised to 4 into 4, this is 64, this is 2 into 2, 4 minus 6 minus 24, this is 20 and that is minus 6. So, again these two are smaller, this is bigger. So, at 2 also it is going to be positive. This is a higher term. At minus 1 again, see here at minus 1 this is plus 4, this is minus 6, so minus 2, this is minus 10 and this is minus 6, so it is going to be negative. At plus 2, minus 2, this is again 64, this is 64, this is going to be minus 24, this is going to be minus 20. So, minus 20, minus 20, 44, minus 6, minus 50 and this is plus 64. So, it is positive. So, now we have this table and now v of minus 2 is calculate the change in sign. One change in sign plus to negative, again one more change in sign 2, 3 and 4. 1, 2, 3, 4. There are 4 changes in sign as we move from value of p at minus 2 to derivative second, third and fourth. Similarly, let us calculate v at minus 1. V at minus 1, 1 change in sign, 2 change in sign and 3 changes in sign. For v0, 1, 2 and 3 change in sign. For v1, no change in sign. For v2, no change in sign. And meaning by that the number of roots in minus 2 to minus 1 will be 4, minus 3, 1. Between minus 1 to 0 no root, 0 to 1 3 or less than 3 by multiple of 2 and 1 to 2 no root. So, this is how our table looks with v at minus 2 as 4, v minus 1 as 3, v0 as 3, v1 as 0 and v2 as 0. And therefore, if we apply Budan's theorem, see the number of roots which may lie in the interval minus 2 to minus 1 are given by v minus 2 minus v minus 1 which is equal to 4 minus 3 equal to 1. And between minus 1 and 0, 3 minus 3 is 0. So, v minus 1 minus v 0 is 0. So, there is no root between minus 1 and 0. Between 0 and 1, v 0 minus v 1 is 3, and that means that the number of roots in 0 to 1 are either 3 or less than that by multiple of 2, means 1 or 3 roots lie in the interval 0 to 1, and again 1 to 2 it is 0 minus 0, V 1 is 0, V 2 is 0, and so there is no root in the interval 1 to 2. So, this is how we can use Budan's theorem to draw the inference. This is what the inference we have drawn, that is, there is one root between minus 1 and minus 2, no root between minus 1 and 0, 1 or 3 roots between 0 and 1, and no root between 1 and 2. So, this is how it gives us the upper bound on the number of roots which may lie in a interval. There is still better result which is known as Sturm's theorem, which gives us exactly the number of roots in an interval. And so, it is able to isolate the roots of a polynomial completely, because no matter what interval you choose, you can apply this theorem to know exactly the number of roots that lie in the interval, that interval. But definitely it requires still more hard work, more harder than the Budan's theorem work. And before we work on this theorem, we will need to understand what is known as Sturm sequence, because this Sturm's theorem makes use of called Sturm sequence. Of course, Sturm sequence is nothing but the sequence of polynomials which are obtained by dividing one polynomial with the other, and the remainder with the remainders we work. It is based on the Euclidean theorem. As we have the Euclidean theorem of numbers, same way we have the Euclidean theorem for the polynomials, and it is based on that. So, for this let us denote p x as the polynomial under question whose roots we want to find. Let us denote by p 0 x, because we are going to generate the sequence, and the derivative of p, which is p dash x, let us call it p 1. These are going to be the first two polynomials in the sequence, and we will use Euclidean theorem to determine the sequence of other remaining polynomials p 2, p 3, so on, till we get the degree of p m x as 0. So, this is how we apply. See, p 0 x, you divide p 0 x by p 1. P 1 is the derivative of p, we know it. P 0 is our original polynomial under quotient. Quotient is q 1, and the remainder, whatever is the remainder, negative of that is p 2 x. Next, we will divide p 1 by p 2, giving us the quotient q 2 and the remainder as minus p 3 x. This process we continue till we get the remainder as 0, that is p n plus 1 will be 0. So, p n minus 1 x is q n x into p n x, and see, this p n x is the greatest common divisor of p 0 x and p 1 x. The Euclidean theorem for polynomials runs exactly parallel as to the Euclidean theorem of the numbers, and the last, the non-zero divisor is the greatest common divisor. So, once we have obtained this Sturm sequence, of course, that is very clear that degree of p I will be less than degree of p I minus 1 x in this case, and the greatest common divisor of p and p dash is p n x. So, this is how we go on, and this sequence we are going to use in determining the number of roots in the interval a to b. So, our sequence is p 0 x is p x, p 1 x is p dash x, p 2 x is the remainder on division of p 0 by p 1. So, that expression if we compare with the previous expression, p 2 x is q 1 into p 1 minus p 0 x, that is nothing but the remainder on obtained on dividing p 0 by p 1. Continue this process, then our p 3 x similarly obtained. In general, p I plus 1 is the remainder of on division of p I minus 1 by p I, and finally, we can say that p n x is the obtained by dividing p n minus 2 by p n minus 1, and the remainder obtained will be our p n x. So, once we have generated this Sturm sequence, and very analogous to the Budan's theorem, the result of for finding the roots of a polynomial in the interval are given by the Sturm's theorem, which states that if V x is the number of changes in the sign of the Sturm sequence, this time we will work not with the derivatives. In Budan's theorem, we work with the derivatives. In the here we will work with the Sturm sequence, which is given by p 0, p 1, p 2, p n, which are nothing but the remainders obtained, that is obtained by division. So, Vx is the number of changes in the sign of the Sturm sequence P0, P1, Pn corresponding to the polynomial Px with real coefficients. Then Px has exactly Va minus Vb distinct real roots in the interval AB. So, Sturm theorem also tells us about the real roots which lie in an interval AB. So, moreover, see in this Px, we any time like P dash, if we can always multiply those polynomial by constant factor. In other words, or which that factor can also involve the variable x, meaning by any time if we have some factor that can be taken out and we can work with the a much more convenient deflated polynomial. So, let us take the example. Let Px be x raised to 5 plus 5x raised to 4 minus 20x square minus 10x plus 2. First thing is, let us find the Sturm sequence. So, the Sturm sequence comes out to be P0 is same as Px. So, it is same x raised to 5 plus 5x to 4 minus 20x square minus 10x plus 2. P1x is the derivative of P. So, it is 5 x raised to 5 derivative 5x raised to 4 plus 5 into x raised to 4 derivative 4x cube gives 20x cube minus x square derivative is 2x. So, minus 40x minus 10 and this is equal to. So, now here in this case see 5 is common, we can divide by 5 and we can work with easier P1 given by x raised to 4 plus 4x cube minus 8x minus 2. Now, to get the further other, see now we need to divide P0 by P1 to get P2, P1 by P2 to get P3 and so on. Either we do it manually or we can use any toolbox, students can use any toolbox to generate it, which will give us, and then we can fractions can be removed because we can multiply by a constant. So, we can multiply by constants to make the coefficients as more convenient. So, P2x is x cube plus 3x square minus 1. P3x in the Sturm sequence comes out to be 3x square plus 7x plus 1 and P4x comes out to be 17x plus 11 and P5x is 1. So, with these then we can try to find the number of roots in the different intervals. We can take minus infinity, if we want to know the number of positive and negative roots, we can take the interval to 0 to infinity and minus infinity to 0 to determine or we can even isolate between different intervals. So, let us work here, see for the interval minus infinity to minus 4, minus 4 to minus 3, minus 3 to minus 2, minus 2 to minus 1, minus 1 to 0, 0 to 1, 1 to 2, 2 to 3, 3 to 4 and 4 to infinity. So, let us work and it is very same as we worked in the Budan's theorem. We need to evaluate these polynomials P0, P1, P2, P3, P4, P5 at these points and these values can be. We do not need to evaluate exactly the value of polynomial at these points. All we are interested is in the sign of polynomial values at these points. So, in the Sturm's theorem, it is a very similar. We have to find the number of changes in sign, but the only thing is now here in this case P0 is our original polynomial Px under question, P1x is the derivative of P, P2x is the remainder obtained on division of P0 by P1. P3 is remainder obtained on division of P1 by P2, P4 is the remainder obtained on division of P2 by P3 and P5 is the remainder obtained on division of P3 by P4. So, these are our polynomials and we will find function v as observing the changes in sign. Like suppose if I want v at minus 4, I will find the whether P0 is positive or negative, P1 is positive or negative, same sequence from P0 to P5 and we will observe the number of changes in sign and that will give us v at minus 4. So, just let us again fill the table, but again rather than filling row wise, let us fill the column wise. So, P5 being constant is 1, it is going to be positive at all the points, we can fill it fast. P4 is 17x plus 11. So, if x is positive, it is all positive, at 0 also it is positive. So, it is positive at all the points. at minus 1, minus 17 plus 11, it becomes minus, and all x negative x is more, then this term is going to be more dominant. So, at all other points of x, it is going to be minus. Come to P3x. P3x is given by 3x square plus 7x plus 1. They are all positive terms. So, for x equal to 0 it is 1, and for x equal to positive this is going to be positive. For x equal to minus 1, so this term is positive, this term is positive, 3 plus 1 4, 4 minus 7 it is negative. For x equal to minus 2, 2 into 2 4 into 2 12, 12 plus 1 13, 13 minus 14 it is going to be negative. For minus 3, 3 raised to 3 9 into 3 27, now this term will become more dominant, x square. So, magnitude of this is going to be higher than this negative term, 3x square will take over 7x for more higher magnitude of x as negative. So, this will become positive for x equal to minus 3, minus 4, minus infinity. Now, let us come to P2x. P2x is x cube plus 3x square minus 1. At 0 it is minus 1, at 1, 1 plus 3, see all this at all positive values it is going to be plus, because minus 1 is the only negative term. So, it is positive for all positive numbers. For x negative, this term will take dominance. Let us see when. X is minus 2, x is minus 1, minus 1, minus 1 2, plus 3, so it is plus. When x is minus 2, minus 8, minus 1 9, minus 9 plus x is minus 2, so 4 into 2 12. So, this will be also plus. X equal to minus 3, it is going to be minus 27, this is also going to be plus 27. So, it is minus, and further x cube will dominate minus 64, this will be only plus 48. So, all these values it is going to be negative. Similarly, we can fill P1, P0, and once we have filled all, our table will look like this. And if we look at like minus infinity, the v minus infinity is 5, v minus 4 is 0, is also 5. So, what does it tell? The difference is 5 minus 5 is 0. So, that means there is no root which is less than minus 4. If we look at the row corresponding to minus 4 and minus 3, v minus 4 is 5, v minus 3 is 4. So, if we subtract v minus 4 minus v minus 3, we get 5 minus 4, that is 1. So, there is one root in the interval minus 3 to minus 4 to minus 3. Minus 3 to minus 2, if we look again, it is 4, the difference is v minus 3 minus v minus 2 is 3 is given by 4 minus 3. So, the difference is 1. Between minus 2 and minus 1, the difference is 0, 3 minus 3 is 0. So, no root lies in the interval minus 1 to minus 2. Between 0 and minus 1, 3 minus 2, the difference is 1. So, one root has to lie between minus 1 to 0. Similarly, 0 to 1, 2 minus 1, so the difference is 1. So, one root lies between 0 and 1, and 1 to 2 difference is again 1. So, one root lies between 1 and 2, and no roots lie between 2 to 3, 3 to 4 and 4 to infinity, meaning by there is no root which is more than 2. So, one root between 1 and 2, one root between 0 and 1, one root between minus 1 and 0, one root between minus 2 and minus 3, and one root between minus 3 and minus 4. So, this is how the Sturm's theorem is able to give us the location of roots within any given interval. The only thing is we need to apply the Euclidean theorem, divide the polynomial and calculate the remainder, but as the degree decreases, this also job becomes easier, but then it gives us a very good picture about the number of roots which lie in an interval. So far what we have learned is about the location of real roots of a polynomial. We know a polynomial with real coefficients can have complex roots also. So, to get a bound on the complex roots, also there are some results available which we will consider in the next module. Not only this, see, once we know the location of the roots, we are able to isolate the roots. See, the next point which we need to consider is that how to find the roots. Because now we know the endpoints of the intervals, like we have done it -2 to -3 or -3 to -4, we can make the endpoint as an initial guess and can apply any of the methods to find the roots, or even there are other special iterative methods applicable for polynomials. There are many such methods. At least one method we will study in our next module. So, bye till then, happy learning, wish you all the best.